First question is, can you guys hear me?
Yep.
Yes.
Okay, and are you seeing my slides?
We're seeing the presenter
Yes.
view, but yeah.
Oh, the presenter view. Okay, let me see if I can change that. I'm using, how about now?
Great.
Okay. So, welcome everybody to this tutorial. And I'm going to talk about some new directions in planning and also use this opportunity to discuss, the current situation that we're in and how it reflects on the concept of planning. Planning has a long history in AI, going back at least 50 or 60 years. Some of the earliest work in planning was done actually not far from where I am. I'm in the San Francisco Bay Area, where it's very sunny and pleasant. It's going to be almost 85 degrees today. We're having a long summer this year. Before I joined Adobe, I directed the SRI AI Center, which used to be called the Stanford Research Institute, but now it's just called SRI International. And some of the first work in AI robotics was done at SRI. You might know about the Stanford robot called Shaky, which introduced this model of planning called strips. Which was the first autonomous robot actually recognized by an IEEE milestone achievement award just 2-3 years ago. And since then, planning has gone on to adapt along with advances in AI. And we've seen over the past decades a number of different ways to formulate planning. For example, planning as solving a satisfiability problem, SAT plan, constraint satisfaction methods, methods that use first order logic, and most recently, of course, the work on probabilistic planning using Markov decision process and reinforcement learning. So what I'm going to talk about has to do with how we enlarge our view of what is planning. And as Anders mentioned, I will talk specifically about ideas like imagination, causality, and creativity, but also tell you some more technical topics, like, for example, how to generalize the concept of optimization, how to plan when you don't have objective functions, and things like that. A lot of the work I'm going to talk about actually was done at UMass before I joined Adobe and before I came out west. I will say a little bit about some of the recent work I'm doing, although I sort of had a more ambitious talk in mind, and then I had to scale back because I realized I couldn't fit it all. So this is roughly the schedule. There'll be 2 sessions, each for about an hour. After each session, we'll have some time for discussion, and then there'll be a break, roughly maybe half an hour, so that, I can get some lunch and maybe you can get tea or coffee or dinner, wherever you are in whichever time zone you're in. And then there'll be a second session, and then we'll have time for some more discussions. So essentially, the topic of my tutorial is we all understand what planning is, and I want to talk about how these other things that we know about, like imagination or creativity or causality, what do they have to do with planning, and why are they important? So this is a statement made by a very famous American general who led the Allied forces in battle, in the defining battle of World War II. And he says why he thought plans were useless, but planning was indispensable. So what did General Eisenhower mean by this? The essential idea here is that when we make plans, we assuming the world will be in a certain way. We're imagining the future, and we assume the world will, behave in a certain way. Unfortunately, that doesn't happen. So a lot of us made plans to, whether you were submitting a paper to ICAPS or maybe attending a workshop or tutorial or just attending ICAPS, you imagine that you will be in France and you would be in this lovely town and you would, maybe do other things. Of course, that didn't happen because of COVID. And so there's a lesson there, which is that planning always assumes an imagined future, but which might not happen. In which case, we can ask the question, why should you plan? If the future is uncertain, why should you plan? And why should you do planning? And that's part of what I want to talk about. So to make things concrete, I thought I would begin with something we're all familiar with. There were at least 2 tutorials yesterday on reinforcement learning. So I'm assuming most of you are familiar with the basic framework of Markov decision processes. This is an old framework. It was developed 60 years ago by Richard Bellman and Ron Howard. Ron Howard did his thesis on Markov decision process at MIT. His thesis was exactly 60 years ago, roughly, 1959, 1960. And Howard introduced the policy iteration algorithm. And this has been the mainstay of work in reinforcement learning for the last several decades. My own exposure to this field came about when I began my research career as a research scientist at IBM Research in the late 80s, early 90s. And I started work on how to design robots that learn. And I published this book in 1992, which was some of the earliest work in reinforcement learning in the context of robotics. And just to give you an idea, those days there was no tech industry, there was no Facebook or Google, there was no web, there were no workstations, there was no Wi-Fi, there were no cell phones. We used symbolic Lisp machines, which probably most of you have never heard of. And the robots were tethered. They had very primitive compute capability, but we still managed to do some interesting experiments. And that was my introduction to this field. So in the Markov decision process framework, we construct plans by solving this optimization problem of mapping every state to a value. So V star is the value of some state X. It's the optimal value and is defined as the best you can do in terms of all your possible actions in that state, which maximizes both the immediate expected reward, which is RXA, plus the discounted future, right? So this is where imagination comes in. We assume that the world will unfold in a certain way and lead us to future states Y with some probability, and then we bootstrap the value of X by looking at the values of adjacent states, right? So a simple example of a linear chain, if the goal is at one end, then through solving this Markov decision process, one can find out that the best thing for the robot to do is to go right. But this depends on a number of things. One is that the goal is not changing. The goals could be changing all the time, in which case you can ask yourself, why do this at all? If at every episode the goal is set in a random place, then what is the value of doing this? What if the world keeps changing? Let's say every episode you get a random graph. What could you do in that such a setting, right? So there are lots and lots of challenges with doing MDP-based planning. But the part that reinforcement learning has successfully solved is where you don't need access to the actual transition probabilities and the rewards, the model of the system. You can sample, assuming the world is a Markov decision process, and then by doing simple statistics, Monte Carlo type methods or bootstrapping methods, you can iteratively solve the Bellman equation. The most common method is Q-learning, where you represent action values, and you're all familiar with this. So in recent years, there's been tremendous excitement over the integration of deep learning and reinforcement learning. And we've all seen impressive demonstrations of deep learning systems solving difficult video games, AlphaGo, solving benchmark problems. But it's useful to remember that even now, the best deep learning systems appear to be no match for humans. And a good example is this paper that was published in AAAI 2007 by Cividis and others, where they did a comparison using random experiments with humans on Amazon Turk, that people are able to learn these games roughly 1,000 times faster than any deep learning system. And I believe that holds true today as well. So you realize that there is something deep and fundamental that these methods are still missing. They take way too long. So the graph here is actually showing the speed at which you're learning the game, and the y-axis is in log scale. So when you see these differences on the y-axis, you have to remember that you're seeing a very large gap between human performance on these games and what these deep learning systems can do. So it's useful to remember this, that deep learning does not solve the reinforcement learning problem by any stretch of the imagination. But there are much deeper problems than this, right? Because the world is not like an Atari video game. There's lots of other challenges going on that we have to understand as well. And that's part of what I want to talk about. So we can think of planning broadly as, these three components. We have the representation of plans, which, for example, in reinforcement learning would be value functions. We have a process of search, where we have the space of all possible value functions, each of which represents a different plan, and we want to find the optimal value function, or maybe some approximation to the optimal value function. And then we have some sort of optimization framework, which in reinforcement learning or MDPs would be dynamic programming, right? The idea that, and in fact, this was a key theorem in Howard's thesis, was that you can iteratively improve your plan. That is, if you haven't found the best value function, there is a one-step improvement process that will find you a better value function. And this is how you bootstrap from an initially poor plan to a better plan, right? So this was integral to how reinforcement learning and MDPs work. So what I'm going to talk about is new representations, new ways to think about optimization, and new ways to think about search as well. So we're all familiar with optimization, right? So in the classic case of optimization, we have a convex function. So just to relate it to what I just talked about, it's well known that you can take Markov decision processes and solve it with linear programming. In fact, that is still one of the most popular methods for solving MDPs in economics and OR. And linear programming is just a convex optimization problem, right? So here we're given some function f, and we want to find its minimum. And there are lots of very good methods for doing that. And this problem has at least a 150 to 200 year history. But it turns out that there are lots of interesting cases when this framework doesn't work, or it just doesn't apply. And surprisingly, most people haven't heard of this. And I hadn't either till the last 10 years or so, when I happened to discover it thanks to the fact that somebody at UMass was a world expert in this topic. And which is this notion of equilibration. So in this equilibration framework, you think of optimization in a very different way. In fact, it's not even optimization. You're thinking of what does it require for some body, for example, in this case, it's a physical body, to be at rest, shaped by the forces of gravity and friction and so on. And the original mathematics for this was developed by a mathematician in Italy called Stampaglia. So we're going to see how to use this in reinforcement learning and planning. But the basic idea is that you move from thinking of functions to vector fields. So on the right, the capital F is a vector field that takes any given state, say X star, and maps it to another vector, right? So vector fields are mappings from vectors to vectors. So the most common vector field we're all familiar with is gradients, right? So I go to the optimization problem on the left and I take a convex function that has gradient, it's differentiable or subdifferentiable. Then at every point in the feasible set, I have a vector field, or I have a vector that tells me the direction in which the function increases or decreases. But on the right, I can have vector fields that don't come from any objective function. And that is the secret to why the framework on the right is more powerful, because it helps us in problems when there may be many different objective functions, or maybe there's no objective function at all. And I'll show you why this is crucial in the formulation that I'll talk about, including in things like imagination. So if you want a deeper dive into this, I'm going to point you to my tutorials. One was given at AAAI a few years ago, and most recently I gave one at the Amherst conference, which was supposed to be in New Zealand, but was also a virtual conference. So this equilibration framework requires solving things called variational inequalities. This was the mathematics that Sampatia established. He actually worked on this for the infinite dimensional case for problems in physics, but it's been adapted to the finite dimensional case. And it very nicely generalizes optimization. Any optimization problem can be solved as a VI, and there are lots of examples where it's better to solve problems using the VI formulation. But it also includes things like games, complementarity problems, complex equilibrium problems like traffic. So if you think of the traffic problem, you have tens of thousands of motorists. In the Bay Area, for example, where I live, traffic congestion is notorious. We have two major highways, 101 and 280 going to San Francisco, and they're always clogged. And so you have a scarce resource, the roads, and lots of drivers, each having different objective functions. And modeling this as a standard optimization problem turns out to be a nightmare. However, it was discovered about 30 years ago that problems like this can be formulated very nicely as variational inequalities. So part of what I want to introduce you to this framework of variational inequalities and show you how you can do this very nicely for complex problems. And then what does it got to do with things like imagination and reinforcement learning? So the basic idea is that we're going to generalize gradient descent. We think of gradient descent as taking the gradient of some smooth differentiable function and walking in the direction of the negative gradient, right? We all know how to do this. And this is the mainstay behind deep learning. So now what we're going to do is we have some vector field capital F, and we're just going to walk in the direction of the negative vector field. Now this vector field may come from the gradient of a differentiable function, in which case it's just optimization, but it might come from something completely different, in which case it doesn't represent optimization, it represents something else. And we'll see why this is a very useful thing to do, even in the case of some of the most popular deep learning models. And then we can generalize these methods. For example, something called extra gradient, where you walk not once, but twice. And why is important to walk twice in the direction of the negative gradient is something I'll explain. So besides this generalization to optimization problems, there's a number of other challenges that I want to touch on briefly. One is, the problem is the world is non-stationary. It's not just that it's stochastic. It changes in a way that is unexpected. And so this poses especially difficult problems for models like reinforcement learning. The world may not be observable. Most interesting real-world problems are only partially observable. And finally, feedback may be very, very sparse, right? These are all challenges that have been addressed by a lot of previous work. And I want to briefly talk about some of the work that I've done and others have done recently in this space. So, for example, sparsity of rewards. One of the reasons deep reinforcement learning is very, very slow is because most of the time it's not getting feedback on how to improve because the problems are such that interesting feedback occurs very late in the game. So there's this notion very popular in psychology of intrinsic rewards, which can substitute for actual rewards, right? So intrinsic rewards are something like drives, which just encourage exploration. And it's well known in animal studies that animals exhibit very characteristic exploration patterns. These are called Levi flight patterns. And they are a very interesting way to explore space because animals don't know where the rewards will be in their environment. The canonical example is a honeybee looking for nectar, for flowers, and the honeybee does not know where they are, so it has to engage in this search process, right? So, but this gives us insight into what we could do with planning, or the process of planning could yield representations that have utility beyond solving specific goals. So this is a very nice book, which if you haven't seen, I highly recommend, by Daniel Pink, called Drive, which is all about intrinsic motivation, right? What is it that motivates people? So the idea of intrinsic motivation is that it is a kind of reward that is not dependent on a task. And it is the basis for most of the creative things that we do. So if you think of what creative people do in all the fields, right? From artists to composers to poets to scientists, there's this drive to do something. And it is not based on external rewards as much as it is based on some sort of internal satisfaction or enjoyment with doing something. And this book catalogs many, many examples where intrinsic drives were discovered to be very important in motivating people. So a few years ago, about 15 years ago, actually, in ICML, I proposed this idea called proto-value functions. So these are task-independent value functions. And they were constructed in a particular way, although as I'll show you, you can construct them in many different ways. But the idea here is that if you're exploring a space, you want to construct pseudo-value functions that nonetheless give you insight into building blocks of behaviors. So in this particular example, we have a simple environment with two rooms connected by a bottleneck door. And what these graphs are showing is particular proto-value functions, which immediately suggest interesting goals for the agent. So for example, if you take the one on the immediate, on the bottom left, it gives you a gradient from the left side of each room to the right side of each room. So if you follow this proto-value function, treating it as if it were a reward function, you would learn interesting policies. And these don't come from specific tasks, they just come from the shape of the environment, right? And so by assembling behaviors that maximize rewards that you get, or intrinsic rewards that you get from just looking at these as pseudo-value functions, you can come up with interesting ways of constructing sort of what you might call proto-plans. In fact, this was done very recently by Marlos Mercado. You might have seen some of his papers in Europe's ICML and so on. And there was a group at Alberta, DeepMind, and other places that followed this up. So this is a very specific way to build it. There are other ways I'll talk about. So the important thing is that these are reward invariant because they're not taking any goals or rewards into account. They just come from the structure of the space. In this particular example, these are orthogonal representations. So each of these has a dot product with any of the other ones of 0. So each one is perpendicular to the other one. You don't have to build them that way. And they're non-hierarchical. These are flat. You can construct them in a different way using multi-scale representations. These were constructed as eigenvectors of a particular graph Laplacian. You don't have to do it that way. You can do it other ways. So in short, what we have is a topological representation. So we start with a Markov decision process, which is defined by a set of states, a transition probability function, and a reward function. We abstract it to a graph. which is a topological representation of this MDP. And then we analyze the graph, for example, by just looking at the adjacency matrix and doing a random walk on the graph, right? And this gives us proto-value functions. So it's important to understand that there's something much deeper going on here, right? Which is that in learning tasks, we not only learn how to do the task, but we learn something of far greater importance, which is the underlying topology of the space. And this is where I've been doing a lot of work recently, which I'm just going to hint at because it requires a whole nother tutorial, in fact. So as I mentioned, there are many ways to build proto-value functions. And here's an interesting one that turns out to be actually completely equivalent, but it was invented before my work by Peter Dayan in the 90s, which is called successor representations. And the idea of a successor representation is very, very simple. You just keep track of the long-term occupation probabilities of every state. Think of it like PageRank, right? When Google does PageRank, it sort of says, what is the probability of visiting a web page if you do a random walk of infinite duration? That's essentially the successor representation. Once you have that, you can just take the dot product of the reward function with that, and you get value function for a particular policy. So the simple math on the left shows you how we can essentially decompose the value function into a dot product of the successor representation and a set of weights, right? So it turns out that recent work has explored whether this is actually plausible as a neural representation. There's lots of encouraging signs that something like this is actually going on in the brain, and there's a lot of interesting work that's exploring this idea. So essentially, you know, this proto-value function idea and successor representations are very, very equivalent. You can mathematically show that they're related in a very precise way. This was shown a few years ago by Stackenfeld. And it's also related to other things that people have talked about in unsupervised learning called slow feature analysis. It turns out, and this is something I unfortunately don't have time to talk about, that all of these are instantiations of something much, much, much more general. And this is the application of algebraic topology to planning. I'll briefly give you an idea of what it's all about. If I look at these objects, I took these pictures from my kitchen. So here's a coffee cup on the right, which I got last year in Italy. It says in Italian that, you know, I've sort of ran out of money in Calabria, so the only thing I could afford is half a cup. It turns out to be exactly the right size for my cappuccino machine that's shown in the middle there. It's my fancy Jura Swiss cappuccino machine, very good for the pandemic. A paper towel holder, and here's this wonderful banana bread that my wife baked. So there's this very interesting idea from psychology that was popularized by Gibson called affordance, where Gibson argued that the goal of perception is not just to see the world, but to understand what opportunities there are for actions in the world, right? So when you see this coffee cup, it's not that you're just seeing the coffee cup, but you understand the topology of the coffee cup so you know where to hold it. And you would hold it entirely differently than you would, for example, if you wanted a slice of banana bread, because the topology of these objects is entirely different. So you can think of taking MDPs and constructing topological representations that go far beyond the graph notion. And this is exactly what I'm working on now. And it builds on some theories that unfortunately I don't have time to explain, but the basic idea is very much the same, which is in the process of planning, you construct these rich representations that then let you transfer learning across tasks and across changes despite the non-stationarity of the environment. And I believe this is something we do and we learn to do from a very early age, and which is why the process of planning is very useful, even if plans turn out to be completely useless, as Eisenhower said. So here's another beautiful saying by Claude Shannon, the inventor of information theory, which is the distinction between the past and the future, right? Which is fundamental to planning, right? We know the past, but we cannot control it, right? So here's an interesting dichotomy. we control the future, or at least we think we can control the future, but we don't know it. And so this is the quandary of planning, right? Because we have data about what's happened in the past, which we can certainly mine, and reinforcement learning systems, particularly deep reinforcement learning systems, extensively mine the data from the past. But we don't know what the future is, and we assume the future looks like the past. So one of the deepest problems in the area is the fact that we don't have access to states, right? So what do we do? And it turns out there's a very rich theory of system identification. And this theory has a long history, which unfortunately has been ignored. It was actually pioneered by people like Schustenberger in the 1960s in algebraic automata theory. It's been rediscovered in AI much, much later as observable operator models, predictive state representations, transformed predictive state representations, and several others. And the basic idea is to construct observable representations of hidden state models, right? So one of the classic examples is called canonical variate analysis. This is a wonderful book by Overshe that I recommend on subspace identification. So the construction involves something called a Henkel matrix. So imagine you have an infinite matrix where the rows represent histories and the columns represent futures. And any particular point in time, like the moment now, is indicated by some particular history and some particular future, right? And you can imagine trying to construct a probability distribution that says conditional on a particular history, what is the predictive or predicted future? And it turns out for problems where there's only a finite number of hidden states, this matrix has finite rank, even though it's an infinite matrix. And so, for example, you can represent these sufficient statistics as the columns of this matrix. So you can discover a basis set of rows and a basis set of columns that let you answer any computation, any query on this matrix. In the PSR literature, these are called tests. In automata theory, they were basically called observable operator representations. And as I said, there's a very, very rich theory on this that if you're interested, you should explore and see where the ideas originally came from. So, so we can certainly build these kinds of system identification models to cope with partial observability. For non-stationarity, the problem is quite difficult. We have a paper that appeared this year's ICML. This is based on a student intern project. Yash Chandak is a PhD student at UMass in what used to be the lab that Anders and I were at, the Autonomous Learning Lab, which is now directed by Phil Thomas. And this paper attempts to extend reinforcement learning to non-stationary worlds where the world is changing. It solves a very special case where the world is changing very, very slowly. So if you think of transition matrices, you think of some sort of Lipschitz smoothness condition that says, you know, the world tomorrow looks like the world today, except for a very small change. And it turns out in those cases, you can construct this model-free representation by essentially data mining the past and looking at how well your policies worked in the past, and then using that to forecast the future so that you learn a policy that is not good for today's model, today's transition matrix, but tomorrow's. Okay, so I won't get into the details of how this works, except to say it works in a very special case, and you can read the paper. So imagination has very much to do with forming representations that don't attempt to capture the world as it is, but as it might be, either in the future or in the past or in some completely, you know, disconnected manner, right? And this is something humans do from a very, very early age. And I believe this has a lot to do with how we do planning. And it has a lot of strengths. Unfortunately, it also has a lot of weaknesses, which are just part and parcel of this process. So to illustrate this, let's look at the unfolding disaster we have on our hands, which is COVID-19. You've probably all know that the US is now facing a large-scale pandemic. More than 8 million people have been infected, and there are at least 220,000 deaths. They're projected to be at least 500,000 deaths by early next year. There is no sign of a vaccine yet. It's not clear when we'll get one. So why has this turned out to be such a complete disaster, right? Why weren't we better prepared? Was it a failure of planning? Was it something else, right? So part of the problem is that the way we think about the future is that we do sampling and then we do rollouts, right? So here's an example where if you look at the election, there is models being constructed every day that says who might win this election. And if you remember from last election 4 years ago, these models were completely wrong. So nobody knows if these models are accurate. The only way we'll know is on November 3rd. And some people think we might not even know then. Why are these models so bad? It's because we're sampling a very small percentage of the population. So if the United States has a population of 300 million people, we sample maybe a few thousand people, usually a lot less. And then we're extrapolating. So it's completely using imagination or statistical imagination to predict a particular future. And we forget that there's a lot of conditions under which this sort of extrapolation might work, and it can often be completely wrong. And this is partly what's happening with our inability to control this pandemic, right? So there's this beautiful book that I recommend in case you haven't seen it called The Black Swan, which talks about the impact of the highly improbable, right? So the COVID-19 is an example of a highly improbable event that nobody saw coming and yet has completely transformed the world, right? It has shattered many economies. Millions and millions of people in the US are without a job. There's tremendous financial disruption. Economies can be viewed as sort of operating under some sort of Nash equilibria where there's production of various goods and consumption, and all of these Nash equilibria have been destroyed at every level, at every industry. So the system is completely drifting. Nobody knows what the new equilibrium will be, right? Just one example would be housing. I live in some of the most expensive real estate in the world, and the housing market here is collapsing because people are fleeing the Bay Area because you can work remotely. Rents in San Francisco have dropped by more than 30% the last few months. If I can work, somewhere in the Midwest and log in, why don't I just do that? So the Black Swan essentially argues that we're ignoring highly improbable events, which turn out to actually be incredibly important. And so standard AI models don't capture this very well, right? And this is part of the problem. Biology has an interesting way to solve problems, which is that evolution decides how to solve problems by essentially some kind of evolutionary game theory. So we have a virus that is much smaller than human DNA and yet can defeat us. It's because it has gone through a long process of figuring out the right plan to overcome our immune system, right? And we just don't have the experience to solve this. And interestingly enough, this year's Nobel Prize in Chemistry went to two women who discovered how bacteria are able to defeat viruses like this using CRISPR technology. And it's essentially this process of evolution that has given bacteria this power, because for 1 billion years they've been fighting viruses. So if you look at this, you see the world is very non-stationary. There's massive competition going on. And so the models that we have currently are very weak, and we don't capture all of this richness. And that's part of the generalizations that I hope you will do. And I'll give you a little taste of some of the ideas that I'm working on. So one problem we have with COVID is that people imagine that they won't fall ill. So this might, you might have seen this. There were 500,000 bikers who gathered in this very small town in South Dakota called Sturgis a few weeks ago. It was the largest gathering of its kind anywhere in the world in the pandemic period. And people were shocked that it was allowed to go ahead. And now we're seeing the fallout because a lot of the people who went there, there's a significant percentage who went back to their home states carrying the infections with them. And this is what's called a super spreader event. So Amos Tversky, who is famous for his work on decision-making, had the statement, which is very interesting. He said, my colleagues study AI, but I study natural stupidity. And you think about this and you realize why this is important, because humans are not the rational decision makers we think. They sometimes make decisions that really shock us. And you ask, why are people doing this? Why are people, for example, 500,000 people going to this event? And it's all because if you think they're using value functions and Q functions, you have to realize that the Q functions that are being estimated are not based on samples that give you some sort of statistical reliability. It's based on imagination. You think, oh, I'm not going to fall ill. The probability of falling ill is very low. Or some people think, oh, it's a hoax. It's not really real. So what drives decision-making by people is not statistics entirely. It's a lot of imagination. And this is fundamentally what is going on, right? So we have to remember that people make decisions for all kinds of reasons, and they're not essentially grounded always in experience because there's just not enough data to do the kinds of grounded decision-making that we need to do. So we see lots and lots of fantasies about COVID on the web. I'm sure you've seen some of these. And why does this happen? Because rumors get spread around on social media and people believe it. People believe it because people imagine all kinds of things. And they're not necessarily grounded in reality. This is just part of how we function as a species. And it's our source of some of our biggest strengths, but also some of our biggest weaknesses, which the COVID virus is exploiting. So one of the things I've been looking at is exactly how does this interference process happen in social networks? And this is part of the machinery I want to talk about, is how to model problems where there's lots of network effects happening, and how do we plan in these kinds of very complex social networks. So to introduce some of the optimization framework, I want to go back to reinforcement learning and talk about projections. Remember that reinforcement learning can be viewed as finding value functions that lie in some space. Typically, we want that space to be nice and smooth, to be in the span of some matrix of basis functions. It's called that phi. So a value function would be a linear combination of the columns of the basis matrix phi. And we can think of methods like temporal difference learning as just finding the fixed point of the Bellman operator T pi applied to our current representation of the value function. So we start with some guess for the value function. We apply the Bellman operator, which is the red edge. And then we're out of the space that we can actually represent. So we project back into the space. And then we find the fixed point. That's an approximate solution to the value function, right? So one very nice way to extend this is to think of proximal mappings. Proximal mappings are generalizations of projections. They were developed by Moreau in the 60s. So if you're given any convex function f, the prox map is the minimization of the value of the function at x plus the vector that is closest to x, right? So a simple example here, if I take the function f to be the indicator function of some convex set, so C here is the convex set, IC of x is the indicator function, which is 0 inside the set and infinity outside. Then the prox map applied to the indicator function just gives you back projection, which is the vector that is in the set that is closest to some vector outside the set. But once you realize that projections are just proximal mappings, then you can just apply proximal mappings. And this is part of a lot of the work that we've done in reinforcement learning recently. The nice thing is that there are many, many, many proximal abstractions that we know, and we can just use these to design new kinds of algorithms. And I'll illustrate some of these later. So there's a very long paper I wrote a few years ago on how to do proximal reinforcement learning or planning in primal dual spaces, and the advantages you get, things like modeling safety, reliability, sparsity, and so on. And it was done with a fair number of PhD students from the Autonomous Learning Lab who are exploring different versions of this. For example, Phil Thomas's work on safety and Beaulieu's work on off-policy reinforcement learning. All of these came out as special cases of this proximal framework. It covers many different algorithms as well. And I want to particularly go into some depth on this idea of doing mirror descent later. So the other theme I want to talk about is causality, right? So what is the connection between causality and planning? So in the COVID pandemic, causality is extremely important. So for example, we want to know if an antiviral drug like a remdesivir can control COVID infections. Right now, there's a huge debate going on because the World Health Organization has said in its very large scale trials, remdesivir had no substantial effect on COVID recovery. The company, which is based in the US, has disputed this, saying its own studies showed that COVID is very beneficial. Remdesivir, in fact, was given to President Trump when he fell ill due to COVID. So there's this huge debate going on. And causality is the problem of trying to discover cause and effect, right? Which is very important in planning as well, except there's very important differences in the way causality theorists think about the world and the way planning typically works. So, for example, we all worry about climate change and want to know to what extent is the pollution that we see a function of things like cars and other things. And it's hard to do this experiment without shutting off the economy. But thanks to COVID, we were able to do the so-called natural experiment. So this is a picture from New Delhi, India, a city where I was actually born. This is a famous place in the city. The picture on the left shows normal air in the city, which is incredibly polluted, in fact, dangerously so. And this is a picture taken much more recently during the COVID lockdown. And it's amazing, you see the difference. So this tells you something about whether, in fact, pollution from vehicles and other sources of pollution is causing the air to be a certain way by doing this sort of experiment, right? We can do this all over the place. We have the incidence of gun violence in the US. Conventional data science, like this article in the Washington Post, basically says how many occurrences of gun violence has occurred in the US since the famous or infamous Columbine shooting. But this is not the most interesting question we want to answer. The interesting question we want to answer is how do we reduce it, right? So what interventions must we do to reduce it? And this is where the debate happens, because people have different sorts of interventions, like strengthen background checks, treat guns like we treat cars, keep guns away from kids. All of these are interventions. President Trump, for example, suggested that we give teachers guns as a way to control gun violence in schools. And so everybody has some idea of how to control it, but this is why it becomes a very difficult problem, because we're trying to discover what is the most effective way to change the current distribution of gun violence. So the difference between causality and planning is that causal inference is really trying to answer the explanation question, right? Why does something happen? Not just as a way to do planning, but for other reasons as well. Often the kinds of things that people in causality study are decisions that are irrevocable, right? So if you give somebody a remdesivir dose, you can't take it back, right? This person has got it. So to understand if remdesivir is causally effective, you need a separate population of individuals who have not been given this drug, right? So that's why in causality, you have typically two groups. We have the control subjects who are not given the drug, and then the treatment subjects who are given the drug. And then you do what's called average treatment effect comparisons between the control group and the treatment group. So this is fundamentally a partially observable problem because the control units have not been given the drug. So you have a counterfactual, which is how would they have recovered if they weren't given the drugs, you know, or they were given the drug, for example. And then the treated units cannot be observed under control. So, for example, President Trump was given remdesivir, so we can ask the question, well, would he have recovered if he had not been given the drug? Well, we don't know that. So it's a problem of figuring out these counterfactuals by doing some sort of imputation. So Rubin introduced the most popular framework for causal inference called potential outcomes. So a potential outcome is a set of possible outcomes that could occur under treatment or no treatment. And the purpose of causal inference is to reason about these counterfactuals or outcomes that you don't observe, right? So a classic example, assumption that is made is called stable unit treatment value assumption. That is the treatment given to a particular individual, the potential outcome for that individual only depends on the treatment to that individual and not to the treatments or lack of treatments to other individuals, right? It turns out in social networks, this assumption is false. So if you're thinking of things like vaccination, you can't assume that Sattva is true because if you vaccinate somebody and they're in, say, in a home where there are other people suffering from the disease, then obviously their outcomes will depend on what happens with these other people as well. So there's a very nice way of thinking about causal inference, essentially completing a matrix, right? And this is, for example, Susan Ethy's work. She's an economist at Stanford. So we think of this matrix as units on the, as the rows and time periods as the columns. And we decompose it into two segments, the control units that weren't given the treatment and the treated units that were given the treatment at some particular point in time, right? So the pink region is what we want to estimate. That is, it is, in a sense, missing data because we want to know what would the outcome have been on the treated units if they had not been given treatment. This is one kind of causal imputation we want to do. And if you're familiar with matrix completion, it's essentially a form of regularization. So you take the observed outcome, in this case, let's call it Y, and you want to estimate the completed matrix Y by essentially taking for example, the nuclear norm, which is the sum of the singular values, turns out to be another proximal mapping. So you can represent this using the proximal framework that I talked about. So here's an example. This is called synthetic control. It's an idea that was proposed by an economist at Harvard named Abadi. So it turns out in around 1989, California passed a proposition called Proposition 99, which levied tax on cigarette sales. And so you have this blue curve, which shows cigarette consumption in California. As you can see, it's declining. And the question you ask is, in this case, California is a treated unit. Was this decline because of the Proposition 99, or would this decline have happened anyway? Now, to answer this question, you have to construct what Abadi calls synthetic control. For example, you look at a lot of different states that didn't pass similar legislation. You look at how tobacco sales changed over these last 30 years in those states, and you construct essentially synthetic versions of control units, and then you do causal imputation, which is a sort of matrix completion problem. And the dotted line is essentially what you see, is that yes, the decline of cigarettes consumption would have happened, but not as dramatically. So that is the counterfactual. So to apply this to reinforcement learning, we can think of filling in Q tables in this way, right? So we have experiences that we have individually for doing actions in the world, but we have Lots of examples where we don't know how to fill in this Q table because we've never done this action. It's a counterfactual. But we can look at control units that have done this action. So for example, a lot of us might not get on a plane or might not go to a particular party or a restaurant in the COVID era because we estimate that Q function by doing some kind of synthetic control, right? We're sort of say, look, these other people actually went and did this and they fell ill. And you impute that on your own experience. And so a lot of the way we solve for these decision-making problems is to do this kind of imagination where we're sort of imagining ourselves in this hypothetical situation and then treating it as our own experience. So, of course, this leads us to imagination as a topic. And there are many, many interesting ways to think about imagination. And I want to relate it directly to causality. Some of you may have seen this book by Pearl called The Book of Why. In it, he describes this three-layer architecture where the bottom layer is essentially standard data science. You observe the world and you form correlations, right? What is the probability of seeing some particular symptom if you know the patient is suffering from COVID, for example, right? The second layer is where you do interventions. You decide to give the patient a drug or not give the patient a drug. And the third layer is explanation. You ask yourself, well, I gave the person the drug, the person didn't recover. Why did that happen, right? So the third layer is what Pearl calls imagination, which is the process of sort of understanding these counterfactuals. So, of course, imagination takes many different forms. A very famous example is this sculpture discovered in Germany, which was carved 40,000 years ago of a hypothetical creature, right? It's got the head of a lion and the shape of a human body. Such a creature doesn't exist in nature, but it was carved. So showing that very, very early on in our history as human beings, we had this capacity to think of impossible things. And this is, why did someone do this? If you think of this as constructing, the process of constructing this object as a plan, there was no value in terms of hunting or anything. This was just an intrinsic drive to build this thing, and shows that this intrinsic mechanism we have is very deep and very old, and we use it all the time. There's been lots of books showing why imagination is a big driver in our everyday life and how that might be uniquely something that humans really do well. This is a famous statement by Einstein saying why imagination is more important than knowledge, particularly in science. And a lot of his work illustrates that idea because a lot of his work was based on thought experiments, which you couldn't actually do because they were completely counterfactual experiments. So you can think of imagination values as kind of an extension of Q learning, right? We think of Q learning as learning action values, which are based on actual trial and error. You get samples and you build Q functions, but you can sort of impute Q values without actually doing experience in the world yourself. For example, you could do synthetic control and impute the values from other agents. You could do some sort of off-policy learning. And later I will talk about some of the work of Elias Barenboim and others on using counterfactual probabilities to estimate these imagination values. So synthetic Q learning would be like Q learning, except we would actually be imputing these Q functions by not just looking at our experience, but other agents' experience. It turns out there's a lot of tricky things you have to be careful about in how you do this. And if you're interested, again, I would point to some of the work that Elias has done in this space. Finally, creativity. What is creativity? The best example is creativity in art. So the painting on the right was by Jean-Michel Basquiat, who's a Bronx graffiti artist, and he died very young in his late 20s, I think. And this particular painting of a skull sold for about $100 million in auction, right? So what is it about this painting that makes it so valuable? And what exactly was Basquiat trying to do in this painting? Essentially, art is, well, art is art. In some sense, you're trying to depict a fantasy, an imaginary situation, if you will. It does not intend to represent reality in any sense. And it evokes certain responses in humans, and its value is what people are willing to pay for it, in a sense, right? So how can we do anything like this? Well, recently there's been remarkable progress in deep learning on these generative adversarial networks. I'm sure you're all familiar with GANs. There's this article in the MIT Technology Review on Ian Goodfellow as the GAN father, or the person who gave machines the gift of imagination. So you can ask, can GANs make machines creative, right? So it turns out you can do interesting kinds of imagination with GANs. This is called style transfer. So if you take a painting like by Monet and you say, well, here's this beautiful painting by Monet. What was the actual scene like that Monet painted? Well, you can use GANs to transform the painting into a digital photograph. And sometimes the pictures look amazingly good. You can construct mythical objects like a zebra and said, if the zebra actually was a horse, what would it look like? It turns out in autonomous driving, GANs are becoming very important because you can't possibly get sample data for driving a car under every possible weather condition. So you drive a car on, say, 101 going from where I live to San Francisco, and you say, well, what if it was completely dark? What if it was raining? What if it was a different condition? And you can't get sample data for every possible condition, but you can use GANs to essentially create hypothetical experiences. And so imagination becomes extremely important in that setting. There's a very interesting connection between GANs and actor-critic. This is a paper by Fao and Vinales at NeurIPS. So we can think of actor-critic as essentially the actor learning a policy and the critic as essentially providing feedback in terms of the value of this policy. GANs are very similar. We have a generator producing sample images, maybe faces, and we have a discriminator comparing the produced output to a sample of real faces and providing a critique, right? So in both cases, you are essentially constructing a two-place function. In GANs, you're trying to maximize the log likelihood of real data and minimizing the log likelihood of fake data. But this is the role of the discriminator. The generator is doing exactly the opposite. And similarly, in actor-critic, you're essentially doing something very similar. What makes these problems difficult is that they involve sort of saddle point kinds of optimization problems, particularly when you want to generalize these architectures, as I'll talk about in a little bit. It turns out optimization becomes very, very difficult in this setting. For example, two of my students did this extension of GANs called GMAN, which turned out to be very useful in building more complicated GANs, such as the ones used by NVIDIA for their very highly detailed face representations, where we have multiple discriminators, right? So instead of one discriminator, you have maybe many. And this graph shows that you basically get better convergence if you add, say, go from one discriminator to 5 discriminators. And there's this work by Sanjeev Arora at Princeton showing that if you had multiple generators and multiple discriminators, you can actually get some, at least weak theory guarantees of convergence. You know, GANs, by and large, there's not much known about the theory of GANs, although lots of people are working on it. So as you ramp up the sophistication of these models, you start getting into difficulty in optimizing. And I want to spend a couple of minutes talking about it and then pause for questions. So the way you think about training GANs is, of course, let's take our workhorse method, which is gradient descent, right? Or gradient descent. And we have these two functions, f and g, and we're doing gradient on each one, right? So one is, say, the discriminator, and one is the generator. And then we're adjusting the weights in proportion to the gradients for each one, right? Unfortunately, this doesn't always work. And the best example is this painting by Maurice Escher called Ascending and Descending. They show two groups of monks. One group of monks is ascending a spiral staircase, and the other group of monks is descending a spiral staircase, but they meet in the middle. This is a visual illusion. You can't obviously do this in the real world, but MCS's painting sort of hoodwinks us into thinking there's something wrong here, right? But if you look at it, you can't figure out exactly what's wrong. How is this possible? Well, you can construct some representation of this for GANs, and here's a very simple example of two functions, f and g. where if you take gradients, you keep going round and round this vector field, whereas the point you should converge to is the center, which you won't. So if you simply follow the gradient in this vector field, you will not solve the problem. And this is the biggest problem with GANs, is that people are just using gradient descent, and it doesn't always work. Particularly as you go to more complex GANs, this model doesn't work. So, so as I mentioned earlier, what we want to go to do is to understand that we're dealing with vector field problems, not simple optimization problems. And we want to apply methods that were developed for vector fields. So this is work I did with one of my former PhD students, Ian Gemp, who's now at Google DeepMind in London. And one of the things that he showed was that, in fact, in these equilibrium problems, you should not go in the steepest descent direction. You should, in fact, go in the direction orthogonal to the steepest descent, which is very counterintuitive. And you can look at his paper on arXiv. So here's an example of a vector field GAN algorithm for a very, very simple GAN model. And he calls this crossing the curl. Essentially, if you think of vector fields, there's this notion called the curl. If you remember your undergraduate calculus, the curl of a vector field is sort of like the rotational component. So it's important to understand the curl and not just the gradient. And once you do that, you can actually construct better GAN algorithms. So we want to take this insight and we want to apply it to far more complex kinds of problems. GANs are a way to build more creative systems, but the standard GAN model, unfortunately, is not good enough. We want something that is more powerful. So for example, if you give GAN samples of faces, it builds new faces, but they're still faces. It's not particularly innovative. It would not do, for example, a Basquiat-like painting. For that, we have to enlarge our notion of what GANs are. So one of the interesting proposals, you might have seen this, is called a creative adversarial network, which is not like a GAN, but it's related. So the way this works, and this was done in particular for paintings, is that it's trained on multiple genres of paintings. You give it Picasso paintings, Rembrandt paintings, Impressionist paintings, and so on. And it's required, the generator is required to produce something that doesn't resemble any of the known styles of paintings it's given, right? It's forced to be creative. And so to do this, you have to first understand what does it mean to be a piece of, a work of art in general. And then how do we measure distance, right? So they solve this in a very particular way by writing this loss function. So it looks very much like a standard GAN loss function. The first term on the two equations that I've written, D for the discriminator and G for the generator, look exactly like GAN functions. The first term basically is log likelihood of real data and minimizing the log likelihood of fake data, right? But then the second terms essentially say, you have this additional constraint. So the generator, the discriminator is basically saying anything the generator produces, I'm going to force it into one of the styles I know, and the discriminator is going to do exactly the opposite. Excuse me, the generator is going to do exactly the opposite. The generator is going to say, I want to produce a style that looks completely different from the styles that were given to me. So you have to sort of learn the style function in addition to producing art. So it was trained on sort of thousands of paintings from all these different styles. And here's some example art that it generated, right? So I'm not an art critic, so I don't know how to value these paintings, but I gave a version of this talk at Berkeley about a year or so ago, and Stuart Russell said, well, clearly it's not art that might, for example, go in the Museum of Modern Art, but people might have this sort of art in their homes, or you might think of putting art like this in hotel rooms. So the next time you're in a hotel room or in some cafe or something, you take a look at the artwork, and it's not particularly innovative. So you can think of that we've managed to solve the creativity problem at this level, maybe produce art that looks sort of vaguely creative, but it's not at the Basquiat level yet, right? So let me pause there and let's take a break. And then in the rest of the presentation, I'm going to get deeper into how do we build these very complex kinds of GAN type of models, and how can we use them. For that, we have to understand a bit more about how to do this more general notion of equilibration that I talked about, and get into some of the details of that. So let's pause here, and I'm happy to take questions for a few minutes before we take a break.
I have a question.
Yeah.
So you've talked a bit about the difference between optimization and equilibration, but I think I don't grasp the real difference on, or why the difference matters, because as you said, in optimization you still have a gradient, you still have a vector field that, for example, in reinforcement learning you have an objective function and you descend and you optimize it. And you said that in equilibration you don't need an objective function, but for example I don't see why that poses an advantage over having an objective function.
Okay, good. So there are sort of two answers to this. One is, even when you have an objective function, it turns out to be an advantage to transform the problem in a different way. So for example, let's take, for example, least squares, right? So we'll take sparse least squares. We know how to solve sparse least squares. It's a convex loss function, right? The first term is essentially the squared difference between the predicted value and the observed value. And the second term is some notion of sparsity, like the L1 norm. And there are a number of ways of solving this using gradients. You know, for the squared part, you take the standard gradient, and then for the L1 norm, you take the subgradient. And it turns out that in the context of reinforcement learning, if you look at sparse reinforcement learning, you have to repeatedly solve these sparse gradient problems every step or every episode for every iteration. And so these algorithms require sort of, you know, they take a lot more time unless you can do what I call warm starts. That is, you essentially are able to initialize your algorithm at the right point. Which is hard to do in the standard optimization framework. But if you transform this into what's called a complementarity problem, which is a special type of variational inequality, you can do warm starts very effectively. And there was a paper by one of my former PhD students, Jeff Johns, with, at the time he was a postdoc with Ron Parr at Duke. So you can look at this paper by Jeff Johns and Ron Parr at NeurIPS, I think it was maybe 5 years ago or so, where they show how to do linear complementarity for sparse policy evaluation and why it works a lot better than, for example, doing something like large TD as an algorithm. So that's one kind of answer, which is, and I'll show you another kind of answer, which is.
So what you're saying is like, for example, you can transform a really complex problem that you're using gradient, such as the traffic problem I think you mentioned, and then you transform it into just a vector field, and it solves much easier, in a much easier way.
Yeah, I will say a little bit more about that in the second half, which is the traffic problem is harder in the sense that traffic problem is an example of a problem for which there is no objective function. If you think of objective functions, what is the objective function? Well, the problem is that it depends on what everybody else is trying to do. So there's congestion on roads. It's very, very difficult to write down objective functions for traffic. And this was discovered by economists a long time ago. In fact, they were struggling on how to solve this problem. And they came up with lots of simplifying assumptions, basically, you know, symmetry in the Hessian and stuff like that. And it turned out that gave you very artificial formulations. And then there was this applied mathematician at Brown who discovered how to represent these as variational inequalities, and that totally transformed the way traffic was modeled. So I'll give you another example in the second half from a problem in economics called spatial price equilibria, where you have a bunch of manufacturers producing some item, and then you have a bunch of consumers. And it turns out, even in that very simple problem, there is no gradient formulation that works. You can't solve it as an optimization problem because the gradient formulation will assume that the Hessians are symmetric, and they're not symmetric. So if you have non-symmetric Hessians, all the standard optimization methods like Newton's method, they all fail. So this is part of the problem, is that, you know,
but
you think
even like complex, well, like method based in backpropagation, like for example, this method that are used in deep learning, like for example, this optimizer like Adam, etc. Like they do a lot of stuff. They calculate covariance, and you know, you do stochastic gradient descent, all of that.
Yeah, none of those will work.
I see.
None of those will work because they all assume at some point symmetry, and symmetry is violated. So you get a problem, right? So the space of problems you can formulate as variational inequalities is a strict superset of the space of problems you can formulate as optimization. So that's the key.
I see, I understand it. Thank you.
Yeah. Any other questions?
There are a couple of questions in the chat, if you look in the chat.
In the chat.
Yes, I can comment on mine. Thank you again for the presentation. It's covered like many angles, and I'm very interested in all of them. So I'm missing the whole aspect of robustness guarantee. I mean, one key aspect of planning is that given these assumptions, this is the plan, and for these assumptions, you're gonna get there, right? But in RL, normally you are solving a different problem that is the expected reward. That is that the expectation that when you try, you're gonna get there, but you might fail for a particular sample, right? So the whole, you basically, I just wanted to ask you about this aspect of robustness of guarantees across this, the whole content you have in Toshin.
So the answer to that question depends on the particular problem you're trying to solve. For example, things like off-policy reinforcement learning or safe reinforcement learning, you can look at the published papers we have that give you the robustness guarantees. Like, for example, there's a paper in the Journal of AI Research that we published, I think a couple of years ago, on off-policy reinforcement learning that shows you the kinds of guarantees you have, you know, for sample complexity and for safe reinforcement learning. There was a NeurIPS paper, and this work actually has been extended recently. There's been a number of further elaborations by people like Li-Hong Li and others showing how to take this dual space formulation and exploit it for other ways. So there's actually a growing literature on this problem.
Yeah, but let me follow up, because you have in the corner like a search, right? And I can imagine, so we have so many search algorithms, so people might say, you know what, I'm gonna embed the state in this representation, deep learning style, and then every time I do a progression, I'm just gonna embed the next state and just keep doing that forever. Trying to do that, it seems that it's not working because probably people try and the results are not published, right? And this is a reason, and in many cases, we have still explicit algorithms, right? You have these distinct states. So then, I was wondering about this sort of distinction when you have are in state or not in the state. I mean, what you mentioned is just when the problem is having these guarantees, but also when we are developing the algorithm, sometimes we want these internal properties that, yes, I know that I'm here, I know I just beyond that, and because of that, I can progress. This is when you do searching planning, you apply an action, and then now you have this proposition that is true, and now you can believe yourself and explore further. Is it become, you know, more compressed, or whatever word we want to use? Sometimes this is hard to know because you might have lost the object in the way because it was embedding in this space. So I was wondering about that. You make this, I mean, you're making a big case here, right? about all these connections. So I was wondering about the implications about this as a follow-up in the internal algorithms. When we're doing searching, it seems that the distinctions are still important.
Yeah, I think you're raising a number of interesting questions. I will say one thing, which is that there's one part of this that I'm not talking about, which actually is very important for planning, which is, you mentioned compactness. So there's been, over the years, a fair amount of work on compact representations for MDPs, right? So for example, if you assume that your transition matrices are represented as dynamic Bayes nets, how can you do planning or reinforcement learning in a factored representation? In fact, Anders himself worked on this for his thesis at UMass. And it turns out there's sort of a puzzle there, which I don't know if anyone's actually ever solved, but which is that when you start out with an initial model of your system, your representation indeed is quite sparse and quite compact, because your reward function might depend on a very small number of state variables. So it's compact. And then each action that you do has a limited effect, right? If you have maybe 1,000 state variables, maybe each action may affect only a very small number of these state variables, right? So this is in the literature of planning, there's been a long set of studies on this problem, going all the way back to things like non-monotonic logic, right? So if I, for example, lift my cup, what changes is the fact that my hand is no longer free because it's holding the cup. The cup is no longer on the table because it's in my hand, but everything else stays the same, right? So the action has a very local effect. If you think of the matrix formulation of this, the matrix is very, very sparse, right? Because it essentially has non-zero entries in a small number of places. Everything else is just the same. Unfortunately, when you unroll these representations over time with planning, you lose compactness. So what people discovered, and this is in a lot of different studies, for example, Craig Boutillier, Daphne Kohler, and Ron Parr wrote a paper on this, is that this value function is no longer sparse when you unroll it. And there's, for example, a counterexample that Ron Parr and Daphne Kohler described in one of their papers. So the hope is that we are able to maintain compactness by essentially rediscovering new representations as we go along. And I'm not talking about that particularly here. I have some ideas on how to do that, but I have not seen this adequately addressed in a lot of work. So unfortunately, it turns out our representations that we know and love, like graphical models, dynamic Bayes nets, assume that the granularity is fixed. That is, the representations are at a particular time scale. But if you think of what long-term imagination or planning, like for example, let's say you're in your 30s and you want to save for retirement, that could be 30 years down the road. None of our representations are very good in modeling problems that occur 30 years down the road, right? Because so much changes. And yet that's exactly where, for example, a lot of long-term investments have to happen, right? You buy a house and you think, oh, well, I want to sell this house maybe 10 years, 15 years, and I expect that I will at least get my money back or I'll make some money. But that requires being able to project into the future and imagine what that future will be 10, 15, 30 years from now. And the standard machinery we have to do those sorts of projections, like graphical models, don't scale well. That is, if they are at the granularity of making, say, weekly predictions, then you unroll them to make a, say, 10-year or 30-year prediction, and they completely blow apart, right? They're not compact anymore. So the only solution to this problem is that you can't have one representation. You have to have a whole scale, multi-scale representations, which I've done some work on. I have some new ideas on how to do that, but I didn't get into that because that's a whole nother topic. Okay. So.
No, just a quick connection there. As a way I understand a lot of the work in in planning, like I'm talking like planning, you have the PDL format, is that the algorithms are creating this approximated over-representation. Like this is heuristics, this is the landmarks, this is what I have so far. And then when you find the solution, if you look at the trace, the proof of the algorithm, it created this partial representation that is not covering everything. First, because reachability. So there are things that you never get there. And second, in other cases, you are compacting whole regions into small things. So, and that depends on one direction is that being informed by the goal. Something is not relevant to the goal, you will never go there. And then sometimes that will simplify the representations. And in other cases, many of the heuristics are also making this compact representation too. So I think that this is probably a space for further collaboration and reading each other people. Thank you very much. I think there are other questions in the chat.
Okay, good. Thank you. All right, so let's take a pause now. It's 12:30 here in California, so let's resume at 12:45. We'll have a slightly shorter break since I ran over a little bit. So let's resume at 12:45, which is 15 minutes from now, and then I'll do the second half of my presentation. Thank you. Okay. Let's begin. And I want to talk about the second half of the presentation. We'll be getting deeper into some of the ideas I talked about in optimization and equilibration and connecting it back to things we talked about. So just to summarize, what we did was talk about imagination, causality, and creativity as three areas that connect to planning. We talked about why plans might be useless, but planning could be useful by building these, for example, topological representations. Why equilibration is important, because a lot of the imagination models like GANs are like actor critic in the sense that you're trying to find an equilibrium between two systems. And we'll see sort of more complex versions of these models that have been studied in economics, where you start to see why you need to enlarge the space of solutions from just thinking of gradient-based optimization to this idea of extra gradient based on vector field representations. And this is something I think that will be very interesting to explore in planning as well. So, so we're familiar with convex optimization as a way of solving MDPs, for example, linear programming, where we have this linear objective function. X is the solution variable, and we're minimizing some linear cost over X. And X itself comes from some polyhedron where it's non-negative and must satisfy a set of equality constraints, right? And this, of course, has been widely used, not just in MDPs, but in economics, OR, game theory, and so on. So just to abstract a little bit, we know convex sets are sets where if I take 2 points in the set and join it by a line, the line lies entirely in the set, which is not true for non-convex problems. And we also know that convex sets are nice because there's this concept of projection, right? If I take a point outside the set, then I can uniquely project it to the closest element within the set. And this is in fact what makes convexity attractive. So a lot of problems can be viewed as finding points that lie between a group of convex sets. These are called convex feasibility problems. In fact, one of the first algorithms for solving convex feasibility problem was proposed by John von Neumann, called alternating projections. And here's an example. I want to find the points in C and D that are closest to each other. I start at some random point y0. I project to one of the sets, say D. And then once I find the closest point to y0 in D, I project that point to the other set C, and I keep alternating between these. And eventually I find the closest points. Right? This is called alternating projections. And this is in fact widely used. This algorithm has been rediscovered dozens of times in different fields. And it's one of the most widely used methods for solving all kinds of problems in many different fields. We know about convex functions. These are functions that essentially satisfy the property that if I take a point, 2 points x and y, and I look at the values of the functions at those points, and then the linear interpolation of those values always lies above the value of the function at the interpolated point, right? So convex optimization builds on these properties, and we want to generalize it in ways that make it easy to solve complex problems, as I'll show how. So let's take a simple example of an indicator set, which is function that defines on a convex set. It's 0 inside the set and 1 outside. There's also an important notion of Bregman divergence, which is that if I take any convex function, for example, here I'm taking the negative entropy function z log z, which as you can see is a convex function. I look at the distance between the predicted value of the function, if you used just the slope of the function at some point, versus the actual value of the function, right? So the distance between x and y, where y is the actual value and x is the predicted value, is called the Bregman divergence. And it turns out that many standard distance functions, almost all standard distance functions you can think about, turn out to be Bregman divergences. So for example, KL divergence is what you get as the Bregman divergence for the positive entropy function. So there's a very powerful generalization of gradient descent called mirror descent, which combines the two ideas that we just talked about. One is the notion of proximal algorithms, and the other is the notion of Bregman divergence. So in mirror descent, you solve the following optimization problem, which is you have some Bregman divergence that is given by d phi, and you try to find the next vector xk plus 1 as the smallest vector x that is has the largest dot product with the gradient of the function at xk and is closest to the point you started. So if xk is the point you started, then the second term gives you the Bregman divergence between xk and any other vector x. And you want the vector x to have the smallest distance from where you started and also has the maximum dot product with the gradient of the function where you started, right? So this might look very strange, except if you plug in for the Bregman divergence, the least squares distance between x and xk, this algorithm just gives you standard gradient descent, right? So gradient descent is just a very special case for the case when the Bregman divergence is just standard L2 norm. If you plug in, for example, KL divergence that we just introduced, then you get an entirely different algorithm, which is called entropic mirror descent. And you can show that for problems, for example, minimizing a convex function over the probability simplex, mirror descent can outperform standard gradient descent by a huge amount, right? The factor is n by log n. N is very large. For example, if you're minimizing a convex function over 1,000,000 dimensions, then you get a huge win by doing entropic mirror descent as opposed to standard gradient descent. So the original mirror descent algorithm was developed by two Russians named Roski and Yudin, who wrote a book on it, but it was not understood very well for a long time. But then Beck and Tabul, two optimization researchers in the early 2000s, clarified what mirror descent was all about, and then everybody understood it. And then there's been a tremendous amount of work in optimization as well as machine learning on using mirror descent. So we can think of mirror descent as doing this idea of called mirror maps, where you start off. You think of gradient descent, you have some, say you're doing backpropagation in neural nets, then the primal space is a set of weight vectors for your neural net, right? And you think of gradients normally as moving between sets of vectors in the primal space. In mirror descent, you do something different. You map from the primal space to the dual space, and the map you choose is a one-to-one onto map. It's a bijective map given by the gradient of some strongly convex function. So here phi is some strongly convex function. You take the gradient of this function. This gives you, from xt, you move to the corresponding gradient of phi of xt. So that is your dual space point. that you started from. You do the gradient step, not in the original space, but in the dual space. And once you finish the gradient step in the dual space, you map back to the original space by doing the inverse mapping, which turns out to be the gradient of the what's called conjugate function to phi. So for gradient methods in Euclidean space, standard gradient methods, phi is just standard least squares, in which case this turns out to be an identity mapping, and the primal and dual spaces are exactly the same. But if you choose something else, for example, if you choose this positive entropy function I told you about, you can get something entirely different. And it turns out to be interesting that an amazing number of different ideas in machine learning can all be viewed as instantiations of this mirror maps idea, including things like multiplicative methods, which have been studied quite extensively, boosting, and a lot of the regularized least squares methods, lasso, least angle regression. Many such methods are all instantiations of mirror descent. One of the surprising things we discovered at UMass a few years ago was that a method like natural gradient, if you remember the work in reinforcement learning on things like natural actor-critic, it's based on this idea that the set of probability distributions describes a manifold. So if you do gradients on a manifold, you shouldn't use the standard Euclidean gradient. You use the Riemannian gradient. It turns out that natural gradient is itself a special case of mirror descent, and we showed that in a NeurIPS paper a few years ago. So Nemirovsky and Newton proposed this idea, which you can think of the dual space as kind of like an imagination space that you project to. So here is the equation. So this is the gradient of some function, f, which I've written in this form because it could be the subdifferential and not just a standard gradient in case the function is convex but not smooth. So you start with the gradient of the function at the initial point. You walk in the direction of the negative gradient. But here you are doing this in the dual space, right? Because xk is the vector in the original space. You apply the gradient of some strongly convex function to it. So you map it to the dual space. This becomes now an operation in the dual space. Then you map back to the original space using the gradient of the conjugate function. In standard Euclidean gradient, del psi and del psi star are identity. So you get back standard Euclidean gradient. But if you use some other strongly convex function, you get something entirely different. So we're going to use this trick for a number of things. In particular, we're going to use it for designing new kinds of algorithms for variational inequalities. So this is the paper I mentioned by Phil Thomas, Will Dabney, and Steve Giguère, PhD students at UMass. It actually came out from a class project in an optimization class that I taught, where we showed that the well-known natural gradient method, which was developed by Amari in the 1980s and widely used in neural nets, is nothing but mirror descent under a particular choice of this primal dual mapping. And if you read the paper, you'll see what that choice is. You just get mirror descent. You just get natural gradient if you plug in that particular choice of primal dual mapping into mirror descent. So we use this to design a safe reinforcement learning algorithm, a safe version of natural actor-critic, which we call projected natural actor-critic, or PNAC. And we showed an interesting simulation of a fairly complex robot from the UMass Perceptual Robotics Laboratory. And we showed that this projected natural critic algorithm, PNAC, was much better than natural actor-critic in terms of its reliability. This particular robot is a difficult robot to control because it has a pendulum, inverted pendulum dynamics. It can easily flop over. And so controlling it safely is a huge challenge. And PNAC does much better than natural actor-critic because PNAC is able to project updates into the safe region where the robot will not fall over. right? And so we showed that PNAC was substantially improved in terms of safety. Okay, so now we want to go to sort of think about this in a slightly more advanced level. And so we want to bring in this idea of doing variational inequalities. So here is the finite dimensional version of variational inequalities, okay? So we're given a convex set of feasible solutions. Just like in linear programming, we have a convex space. So these are all vectors that are potential solutions. Think of it as, you know, vectors for some reinforcement learning problem if you want. And we're given a vector field, capital F. Now this might come from the gradient of some standard loss function. So if you're doing sparse reinforcement learning, this would be the Bellman error plus the L1 norm, right, term. So that could be, the gradient of that would be capital F. If you're doing off-policy reinforcement learning, then capital F would be the projected Bellman error that you use in off-policy reinforcement learning, like gradient TD, for example. But in general, capital F might not correspond to any standard objective function, or might correspond to many objective functions, as we'll see. So what is the goal in solving a variational inequality? You want to find a distinguished vector called X star at which the following property is true. The vector field at X star makes an acute angle with all vectors of the form X minus X star. So here is X star. Here is the gradient at F of X star, the vector field, excuse me, at F of X star, is F of X star. Here's a vector X minus X star. So this angle must be less than or equal to 90 degrees. And you can see, because the feasible space is convex, it guarantees that there is such a point. Now, this might seem a really strange condition, but if you look at this for a minute and you say, well, what if this vector field came from the gradient of some function, right? Then you get back the standard condition for when X star is the minimum of a function. This is in fact exactly the condition for minimum of a function. And so every optimization problem is essentially a variational inequality problem. But of course, variational inequalities also handle the case when capital F does not come from the gradient of some scalar function. So you can show a number of cases. For example, all game theory problems are variational inequalities. If I take a sort of standard prisoner's dilemma or some other kinds of game theory problems, this year's Nobel Prize, for example, went to 2 Stanford economists for their work in game theory. So in a standard, what's called Cournot-Nash game, you have M players. Every player has some strategy XI that should belongs to here. There's a joint payoff. So ith player has a payoff, which is a function of everybody's strategy. Then we think a set of strategies, which could be a mixed strategy, not just a deterministic, but it could be a stochastic strategy. X star is a Nash equilibrium if the following condition is true, and this is in fact exactly a variational inequality. So here's a summary of the difference between optimization and variational inequalities. In optimization, we think of the notion of convexity. The analogous notion in variational inequalities is the property of monotonicity of the vector field. The Jacobian in optimization is typically positive, definite, and symmetric. In variational inequalities, you can have asymmetric Jacobians. You have a single optimization function in optimization. In variational inequalities, you may have many optimization functions, or in fact, none. So just to give you a little bit of background on what are monotone operators, which is extension of convex functions, think of a relation on n-dimensional vector space as monotone if the following property is true. So if I take 2 pairs in the relation, right? X is in the domain of the relation and U is in the range. Similarly, Y is in the domain of the relation and V is in the range. If I take the difference between the domain elements and the range elements, right? X minus Y and U minus V, their dot product should be greater than or equal to 0, which means it should be, they should form an angle that is less than or equal to 90 degrees, right? This is the property of a monotone operation. You can show, for example, things like if you take the subdifferential of a function, convex function, that satisfies the monotone property. It just comes about from the standard definition. So you can look at standard books on this. This is covered in, for example, things like Boyd's book and so on. So if you're not familiar with subdifferentials, this is the extension of the notion of a differential or a gradient. The subdifferential of a function f at x is the set of all vectors v such that the gradient property is satisfied, right? That is, if I take the dot product of v with z minus x at some point z, then the value of the function at z is greater than equal to the value of the function at x plus the dot product of v and z minus x. So think of this as, if you think of the standard gradient, then this, you would plug in the standard gradient here, except here you may have many gradients at a single point. So typically when you think of the gradient of a function, you think of that as a unique point. Here the gradient may not be unique. So for example, if I take the indicator function, which is not smoothly differentiable, because it's 0 inside the set and infinity outside, and I ask what is the subdifferential of the indicator function at some point x, say the vertex here, you get what is called the normal cone, which is all of these points. And you can show that by just looking at the definition of the indicator function here. Remember, for all points inside the indicator function is 0, and all points outside it's infinity. So if you plug that in here, you will get exactly the normal cone. Okay, so you can generalize optimization to what's called the monotone inclusion problem, which is instead of minimizing a function, you can find an element 0 of a monotone operator. And it turns out to be exactly analogous to optimization. And so VIs can be viewed as a monotone inclusion problem in the following sense. Okay, so here's a sort of a high-level view. So we can think of the broad space of what are called monotone inclusion problems as an extension of optimization problems. And then you can think of special cases, for example, things called operator splitting. Then you get standard optimization problems like dual decomposition, alternating direction method of multipliers, which is a very nice way to think of a lot of machine learning problems. There's a very long tutorial paper by Boyd on this. We can think of mirror descent. So all of this comes as a special case of these monotone inclusion problems. So to make things more concrete, let me give you an example. It's a very standard problem in economics called spatial price equilibria. And this is a simple enough problem to show why standard optimization doesn't work here. Okay, so imagine you have a set of manufacturers given by these blue nodes, right? So if you're thinking about GANs, you can think of these as generators, right? So these manufacturers produce stuff. For GANs, these would be, for example, candidate face images. But you can think of these as maybe, milk. People, farms that produce milk. And the green nodes are consumers. They may be grocery stores or individual consumers, right? So when you have an edge from a manufacturer to consumer, you basically mean you're capturing the amount of trade that happens between this manufacturer and this consumer, right? So the strength of this is going to depend on how much of, say, milk that this consumer buys from this manufacturer. Now, these manufacturers are all competing with each other, right? They all want most of the business. So, but they have to basically try to recover their costs, which is they're not going to be giving milk away for free. So each manufacturer sets a certain price for milk. But then there's a certain transportation cost because the milk has to be, produced and then shipped over to a particular consumer or grocery store. So there's a cost of transportation. So you need to have a certain equilibrium condition, which basically says that the cost of manufacture plus the cost of transportation cannot be less than the price that the consumer is willing to pay, because otherwise there'll be no trade, right? So this is the equilibrium condition you want to satisfy. And it turns out that this equilibrium condition can be captured as a variational inequality. So it essentially goes like this. We have the following parameters of this problem, right? The supply level, how much milk is available from the ith manufacturer, how much the ith manufacturer wants for supplying milk, how much demand is there, so each consumer or grocery store may require a different amount, how much they're willing to pay, and the cost of transportation, right? So this gives the equilibrium condition I just said, which is the cost of manufacture and transportation cannot be smaller than the demand price. Otherwise, there won't be any trade. And you can take all of that and you can write it as this type of variational inequality, okay? So a good source for understanding variation inequalities is Anna Nagurny is a professor at UMass, Amherst in the management school, and she's written a book on network economics. She also has a lot of tutorial papers on her webpage. So if you just go to her webpage at UMass, you'll find her papers. So why can't we solve this as an optimization problem? It turns out you can only solve it as an optimization problem if the following conditions are true, which is essentially requiring collusion among the manufacturers, which is not true in general, right? So if I take the gradient of the supply price for the ith manufacturer with respect to the supply level of the kth manufacturer, that must be equal to the gradient of the supply price of the kth manufacturer with respect to the ith supply level of the ith manufacturer. There's no reason for this condition to be true because the manufacturers are in competition, they're not collaborating. So you can show the same thing about demand price. So in general, this problem violates the symmetry condition, which is needed for you to pose it as an optimization problem. And this is a characteristic of many problems in variation inequalities where you have these symmetry violations. And that's why posing these problems as optimization problems doesn't really work. You can show that all optimization problems are essentially VIs. As I mentioned, the standard gradient condition that you get for optimization is just a special case of a variation inequality. You can show that certain classes of VIs reduce to optimization when the gradient, the Jacobian of this vector field is symmetric positive definite, okay? Under this condition of symmetry and positive semi-definiteness of this Jacobian, it turns out that you can show that there is always an objective function whose gradient gives you back the capital F vector field. So this is interesting because it shows that you can start with some vector field, and if it so happens that the Jacobian of this vector field is symmetric positive definite, there must be this scalar objective function whose gradient gives you back the vector field here. But this is not true in general. So the simple way to solve variation inequalities is what I mentioned as the equivalent of gradient, which is simply walk in the direction of the negative vector field. So you start at some point, say z, then you look at the direction of the vector field at z, which is f of z, and you walk in the negative direction. So it's becomes z minus f of z times some learning rate. If that takes you outside the space of allowed solutions, you project back on the space. So imagine the space of allowed is this convex sect, namely a circle. You start at z, you project the direction. So in this case, the tangent of the vector field at this point is this. You project out, you go back, and you ask yourself the question, am I at the same point I started? If I am, I've solved the problem. Otherwise, I do the same process. And you can show this doesn't work because what's going to happen is that every time you will go along the tangent, then you'll project back, you will go along the tangent, you'll project back, you'll go along the tangent, you'll project back, and you'll keep going around and around in the circle, but you'll never get to the origin, which is where the solution lies. So the vector field in this case is given by this, right? F of xy is simply y and minus x. This example comes from this very nice book by Boutsikas and Tsitsiklis called Parallel and Distributed Computation, which has a section on variation inequalities. Okay, so there was this very nice algorithm by Korpolovich in the mid-1970s called the extra gradient method. It's very clever. It's called extra gradient because you do the effect of one additional gradient step, right? So imagine I'm starting at some solution point, xk. I walk in the direction of the negative gradient, a negative vector field at xk, which is minus f of xk. If that takes me outside the space, I project back. This is yk. I again walk in the direction of the negative vector field at yk, which is this. And then I go back and I say, that is the direction I'm going to move in from my original point. So you're looking ahead one step and you're pretending that the sort of direction you should move in is not the gradient, negative gradient at that point, but at the next point. This seems like a very simple change, but it turns out this solves the problem we just solved. Because if you go back here and you realize that if you went in the direction of the negative vector field at this point, you projected here, now you go in the direction of the negative vector field here at the second step, and then you go back here and go in the direction of the negative vector field that is parallel to this, then you will not go around in the circle. You'll start converging. Slowly, you'll converge to the center, right? So that's the trick. So now we can combine this idea with mirrored descent. And this is an algorithm that was designed by Nemirovsky just a few years ago called MirrorProx, where you do this mirror descent idea, but on the extra gradient algorithm, not the gradient algorithm, right? So again, once you start in the primal space xk, you project, you map it to the dual space using the gradient of some strongly convex function. Now in the dual space, you do the extra gradient step, not just the gradient step. And once you're finished, you map back using the gradient of the dual function. And this algorithm has a lot of nice properties. One of the things we did was we showed how to design very good off-policy gradient TD algorithms using this. And this is the topic of Beaulieu's PhD dissertation at UMass. So now we can actually use this to design new algorithms for variational inequalities. And this is work that Ian Gemp did with me, and we wrote it up for publication in a couple of places, mostly AAAI workshops and spring symposia and stuff. I won't get through all the details of the algorithm because it's a little complicated, but essentially it hinges on sort of doing this mirror descent extra gradient, except Ian comes from a background in applied mathematics. So he brought in this idea of doing Runge-Kutta kinds of steps. You know, Runge-Kutta, if you think about solving ordinary differential equations, what you do is you take a step in numerically solving an ordinary differential equation, and then ordinary differential equation, you're given the gradient of some function. So y is, the rate of change of some variable y is given by some function of x. And then you walk for a certain distance in the space and you look at the gradient of the next step. In Runge-Kutta, you do all kinds of half steps and quarter steps and so on. So this is standard Runge-Kutta gradient descent, right? So instead of just walking in the direction of the gradient for the full step, you do all these half steps and so on. And then there is a way of combining all of these estimates into one common estimate, which is what Runge-Kutta methods do in standard gradient descent. So you can do this for mirror descent, right? You can, instead of doing standard gradient descent Runge-Kutta, you can do non-Euclidean extra gradient Runge-Kutta. And that's what Ian did for solving these variational inequalities. You can find the details in these papers and his thesis at UMass. So we want to solve complex variational inequality problems, in particular, very complex planning problems, such as this internet model that Anna Nagurny and colleagues proposed a few years ago. You can think of this as a very complicated kind of GAN, right? So imagine you have this network, and at the top are like generators like a GAN, right? Except these are service providers of some service, right? They're basically generators of content. So if you want to think of this as video distribution, you can think of each of these nodes. For example, this could be Netflix at the top, and this could be Amazon Prime, it could be Hulu, Vudu, and so on. There are now Disney Plus, Apple TV. There are dozens and dozens of streaming channels, right? They're all like GAN generators. They are producing content for you. At the bottom, you have demand markets, you, me, everybody. And we have to choose to get our content from one of these service providers, right? But these service providers have to rely on these middle agents, right? These are the network providers. So if you want to watch, for example, Netflix on your iPhone or Android phone, you need a network provider. In the United States, you might have AT&T or T-Mobile. In Europe, you may have Vodafone, and in India, you might have, Geo or something else. And so you need a network provider in addition to the content provider, right? So the game, it's a very complex game that is being played out between service providers competing with each other and network providers competing with each other. And it's very, very difficult to write down an objective function for this whole game, right? Because it depends on the interaction of all of these agents. And it's very complicated. But you can solve this as a variational inequality. And this is exactly what Anandagurni did in a paper that she wrote a few years ago. What we did is we showed that Ian's algorithm is able to solve very large versions of these. So one of the questions for the planning community would be how to use this idea to design new kinds of planning algorithms, which I'll leave you to think about. So I won't get into all the details of the planning formula, the problem formulation. You can see that from our paper, Anandagurni's original paper. But essentially, it's the standard kind of thing you would expect, which is how, for example, Q measures how much content is flowing from content provider I to some customer K via some network provider J. So this could be, I could be Netflix, K could be me, and J could be AT&T, which is my network provider, right? For you, it might be Amazon Prime, it could be Vodafone, and you could be in Europe, for example, right? So, and then, you have things like how much content is available, what is the quality of service you desire, what is the price that they're charging for the content, how much does your network provider charge for bandwidth, and so on and so forth. All of these variables go into this. And you can package all of these variables and write out some, sort of a giant variational inequality that combines all of these terms, okay? And it turns out, this new algorithm that we came up with, or I should say Ian did most of the work on this, actually does really well in some of the limited problems we looked at. So we started with problems of size 10 and went up to problems of 10,000 roughly. And it seems in terms of what we're plotting here is the number of iterations to convergence. It seems remarkably scale-free. Scale-free means the convergence of this algorithm doesn't seem to depend too much on dimension, although the running time obviously grows as the dimension grows. Interestingly, this is exactly the property of mirror descent, right? Mirror descent by Nemrowski and Newton was proposed precisely as a scale-free algorithm, because you have this very weak dependence on dimension in mirror descent. And that's exactly what we're seeing here, is that convergence in terms of the number of iterations doesn't seem to depend a whole lot on problem size. And that's not true for standard extragradient, or if you do standard sort of Euler or other methods for solving this. So we solved a number of other problems as well. One of the problems that we looked at, which would be actually very interesting for COVID, because you can adapt it to the COVID problem, is the blood banking, right? So blood is a very interesting challenge, because in order to do surgeries in any hospital in the world, you need blood. And blood is a very perishable quantity, right? And blood is not easily manufactured. You need donors. So essentially what happens in the US and in India and lots of other places is you have different organizations, for example, the Red Cross, companies, for example, Adobe has blood drives, universities do blood drives. So you essentially have a bunch of places that collect blood. And then once the blood is collected, it has to be processed. And so there are blood centers that pick up the blood, there are component labs that process the blood, there are storage facilities, there are distribution facilities, and finally there are hospitals where the blood is actually delivered and used. Now, it turns out this is a huge challenge because, for example, it was shown just a few years ago that the supply of blood in the US is just like 3 days. We just have 3 days of supply of blood. And many elective surgeries in hospitals have been canceled because there wasn't enough blood. So it's a very challenging problem. And again, you know, it turns out algorithm does really well. We took a model that was proposed in one of Anna Nagurni's papers. And once again, we showed that it has this scale-free property. In this case, I think we went up from problems of a size 10 to a problem of size million. And while the running time of the algorithm does increase, it seems remarkably robust in terms of the dimensionality of the problem. This is just showing running time, which scales proportional to the size of the problem. Finally, the final example I'll give is sustainable supply chain manufacturing, where you have a bunch of firms making products and you want to do this in a sustainable way, which means you want to minimize the amount of wastage. And supply chains is the reason why, for example, no matter where you are in the world, you can get fresh produce, right? You could be, you know, in the middle of, for example, in Amherst, we have long New England winters, whereas there's lots of snow on the ground, but you can go to the grocery store and pick up, you know, any kind of vegetable or fruit. And it's because the supply chains that are delivering all of that, you know, sometimes over long distances, right? And so this is exactly sort of setting up the supply chain problem as a very large variational inequality. Again, you have lots of firms competing with each other, the transportation agents, and there's lots of costs involved in shipping and storage and all of that. Again, we see a very, very similar pattern where the previous algorithms take longer and longer to converge as the problem size increases, and our algorithm is remarkably stable. Of course, we incur greater running time costs, but in terms of iteration to convergence, we get the scale-free property that mirror descent has. Okay, so I've got about 15 minutes more. And so what I wanted to do was briefly go back to causality again, and then connect it back to reinforcement learning, and then we can just have a final discussion. So if you want to think about the problem of counterfactuals, which is really what causal reasoning is all about, you should think about it as an extension of the standard notion of conditional probabilities. And this is very nicely described in one of Pearl's, you can read any of Pearl's books, but the one I would recommend is Causal Representations in Statistics, which is a very nice short summary of his work. So the way to think about this is that we have variables like X and Y. So if you think of X as being some action and Y being some outcome, okay? Or you can think of X as being some medical observation and Y being some measurement, some symptom that we're measuring, right? So in this case, we observed some value of X, let's call it X prime, and the corresponding value of Y was Y prime, right? So if this was a particular action you took, Y was the outcome under that action. But we're asking the following condition: what if X prime didn't have this value, but it had some other value, let's call it X? What would be the counterfactual value of Y? So this is like saying, for example, President Trump was administered remdesivir, right? That's X prime. And Y prime was he recovered fairly quickly in 3 days or something. So X says, what if he wasn't given remdesivir? What would Y be? Would he have recovered in 3 days, or would he have not recovered, or would he have taken longer? That's what we're trying to estimate, right? So the reason this is difficult is because there are two possible worlds here in conflict, right? In this world, X takes on the value X prime, for which the outcome is Y prime. And in this world, they take on different values, right? So when you want to reason and you think of, for example, applying Bayes' rule here, in Bayes' rule, you take the antecedent and the consequent and you join them, right? So this would become Y given Y of X and this. So you're conflating two possible worlds, which in standard probability theory is very hard to do, right? Because the assignments to these variables are in conflict. So if you do standard graphical models, it doesn't work because you've already decided the value of X is X prime. And now you're saying, well, what if it was something else? You can't do that in the same model. So in this counterfactual setting, you can actually do it. And the reason you can do it is because of the do calculus representation that Paul uses. And so given that we have this machinery, you can say, how can I do counterfactual Q-learning, for example? So, and that's actually not that difficult to understand because instead of the standard transition probabilities that we have in Q-learning, where you would say, what is the probability of seeing some new state conditioned on the previous state and some action, we would sort of ask the counterfactual question that says, well, we had some old state when we did some action, but now we're contemplating some other action and what would be the new state that we would have gotten to if in fact we had done this other action, right? So that's counterfactual Q-learning. And you can construct counterfactual Q values. So that's actually exactly what Elias did. I'm going to show you just the simple version of that for bandits, and then I'll show you the Q-learning version. So remember, bandit problems are like simple reinforcement learning problems where there's no state, right? So you have just a set of actions or arms. You can pull the arm, and you want to discover the arm that has the highest, say, average payoff, right? So standard way to solve bandits is to do something like Thompson sampling, which is what a lot of people have been doing. But now imagine a version of bandits where there are this partial observability, so the unobserved confounder. So you can't actually see all the state variables that you need to see, right? So it turns out in that case, doing the sort of imagination kind of counterfactual estimates gets you a better algorithm. So the way this works is to say, if my greedy policy said do action I, and I condition on that, but then explore deviations from that, right? So I choose some other action A. This says, what is the probability that my outcome would be one that is better than what I might have gotten if I had stuck with my policy, right? So basically it says, play the arm that maximizes the counterfactual estimate of the reward if you choose some action other than what your greedy policy suggests, right? And this paper by Forney, Pearl, and Barenboim goes through the conditions under which this is true. So they come up with this fairly contrived example, I would say. Essentially, this is a casino in Las Vegas where the casinos discovered that they can fool the gamblers and the gambling commission by rigging up their machines in a particular way. So what they do is they look at, they detect if the gambler is drunk or not drunk, okay? And they can have the machines blink lights or not blink lights. And by playing with those conditions, they can construct payoffs in such a way that if you just did a randomized trial, let's say the gambling commission comes and says that the payoffs have to be even. So there can't be, it's got to be a 50-50 chance that the gamblers will lose or the casino wins, right? They can rig up the probabilities in such a way that if you just did a randomized trial, you will think that the machines are fair, but actually the machines are not fair. And the standard bandit algorithms like Thompson sampling will never discover this, right? But it turns out this counterfactual thing using imagination where you say, well, I know my instinct tells me, in the paper, I think they use the word intuition. Intuition tells me I should play this arm, but I'm going to deviate from it and play this other arm. and you can discover a better policy this way. They've explored other versions of this. For example, imitation learning. So I mentioned that often you want to learn from other agents. The problem with learning from other agents is that you don't have access to their state. So if you see another agent doing an action, you see the action, but not all the antecedents that led to that action being chosen, right? For example, and this is important in things like clinical trials, right? If you're doing a clinical trial and you observe the physician recommending some treatment, you might not know that the physician is using covariates other than what's in the patient's medical history. For example, maybe the physician is responding to emotional state of the patient, or the fact that the patient cannot afford certain drugs, and that's not recorded in their medical history, right? How much they can afford to pay. So you might be led to the completely wrong conclusions if you just did blind imitation learning. But by decomposing your counterfactual estimates into this observational component, as well as this causal experimental component, you can actually discover the differences, and then you can do better imitation learning. And there's written a number of papers, including, I think, there was a Neuroscience paper last year. And there's an ICML paper this year on dynamic treatment planning, which, hinges on the same idea. So there was a long archive paper, which I think is not there anymore, but Elias tells me that they have a new version that might already be released on his webpage, where they looked at this, what I would call intermediate point between standard fully observable MDPs and POMDPs. And these are MDPs with unobserved confounders. But there's some strange kind of Markov property that still holds, but it's not a full POMDP, and yet you have some sort of partial observability. So it's a very strange model. So here it is. Here's states, right? The standard state model. You have states. There's a chain of states. Your policy is conditioned on the state, and here's the action, right? But then there's these other variables that you don't get to observe. And the policy is not just a functional state, but also these unobserved confounders, okay? So for example, if this is medical treatment planning, S could be the medical history, pi is whatever policy the physician is using for recommending some treatment, which is the action. But unbeknownst to you, the physician is not only looking at the medical history of the patient, but also variables like emotional state of the patient, or how much can the patient pay, or something that is not recorded in the medical history, right? It turns out in such cases, counterfactual Q learning works better than standard Q learning. And that's the sort of the core conclusion. So in a sense, imagination works here because you allow yourself to depart from the greedy policy that is conditioned purely on the state. So they don't use this word imagination values, but I do because I kind of like it. But this is the way it decomposes, right? So the imagination value is like a Q value, but over more terms, right? So this is a state at time t. This is the action you should take. Your policy tells you to take this. This is the deviation, right? This is the counterfactual action, A t prime. And in understanding this, they use this counterfactual representation of counterfactual probabilities that I just explained, right? So they write down the value function decomposition using counterfactual probabilities, and then the rest is all standard Q learning. It turns out a very, very simple way to understand what they're doing is that if you treat the state as not just the regular state, but the combination of the state and the action, and that becomes your new state, then if you did standard Q learning over the state SDAT and treat AT prime as your actions, you get the equivalent of what they're doing. So a very simple way to understand what they're doing is they just redefine what state is to be not just state, but state and actions. And then there is a third term, which is actually the new actions you're considering, right? This turns out to be equivalent to what they're doing. Okay, so let's stop there. So essentially, to summarize, I talked about things like causal representations in planning, imagination, and some amount of how you can get creativity, and how planning is much more than plans. Planning is just a way of building long-term representations that can transfer. You can do this by doing topological representations. You can do this by building these causal representations. And then by doing clever search using mirror descent in dual spaces, you can design really scalable reinforcement learning algorithms, as well as algorithms for solving complex planning problems like variational inequality, like equilibrium problems I showed, that seem to have this scale-free property, which seems very, very interesting. So an interesting question for the folks in the planning community is, how do you design standard planning algorithms in this way so that you get the scale-free property? And VIs are very attractive because there are lots of complex problems where it's difficult to write down simple objective functions, right? Whenever you have competing objectives, the world gets very complicated. And it's particularly true for social networks, right? We see today social networks have created an alarming amount of discord in the United States and everywhere else in the world. We find fringe communities that believe all sorts of crazy theories. And you wonder, how is it possible that people hold such views? It's just that they're part of this subgroup where everyone seems to hold this view. And so this is a problem that has been studied in social science and social networks for a long time. It's called opinion dynamics. How is it that you can have views that are completely untrue? It's just because your views are reinforced by everybody that you talk to. And so you tend to believe those views because everybody around you holds those views. And you think that must be true. And you never get out of this little subgroup. And so you end up with these countercultures being formed. So this poses a lot of huge challenges for how we think about AI in the years to come. So GANs are one of the, I would say, most exciting developments in deep learning in recent years. It's probably the only new thing in deep learning, I would say, aside from sort of the feed-forward backpropagation idea that was developed in the mid-1980s. And GANs show how to do imagination. There are, I think, lots of very cool extensions of GANs, but they require going beyond how people train GANs, which is a standard gradient descent idea. I don't think is the right way to train complex kind of GAN models. And so with Ian, we explored variation inequalities again as a way of doing training of GANs and other more complex kinds of things. But we think that this framework is useful in many other settings as well. And it's underappreciated in AI because most people don't know about this tool that economists have been working with for, I think, now several decades, but it's just not percolated into AI. So hopefully you will use this as motivation to maybe explore a little bit about variational inequalities. Since now, like me, most of you are working from home, so you may have more time on your hands to read. As far as I'm concerned, the Bay Area where I live, I'm close to the headquarters of Apple, Google, Facebook, NVIDIA, Adobe, many other companies, and are all in lockdown mode till well into the end of next year at this point. And some companies are realizing that they're going to be permanently having the option of working from home. So COVID has changed many things. It's brought about a completely new world. And so we have to completely replan in this new world. Okay, so let me stop there. Thank you.
Okay, thank you very much, Sridhar. So we have time for more questions if anyone has other questions to ask.
probably pretty late. How late is it for you, Anders?
Yeah, it's close to 11 o'clock at night here.
Oh my goodness.
Because this is being recorded, probably people plan to watch the recording after the fact.
Yeah, no, I understand. I mean, this must be hard for many people. So you know, if there are no questions, I wouldn't get upset. I mean, it's just very hard to do this. You know, we were all supposed to be in France, and I was looking forward to that trip. So let's hope next year ICAPS actually does happen. You know, without it being virtual, but we don't know yet.
No, I think the discussion after the first session was very good. So I think at least we got some good questions asked, and I really enjoyed the tutorial. I think you bring up some interesting perspectives on things that are useful to think about.
Yeah, and you know, the process of doing this tutorial was very helpful to me as well. And while doing this tutorial, I realized that lots of interesting things that I hadn't thought about, and so for me, the most useful thing was you know, putting it all together and then thinking about things that I could work on just as a consequence of writing up these slides. So.
Okay, so if there are no questions, we will call an end to this session. Thank you very much, Sridhar, again for your time and for your presentation.
Okay, great. Thanks a lot.
We'll continue the conference with workshops tomorrow.
Okay, thank you. Good night.